Finally, let's take a look at satellite imagery and how to interpret various types of satellite pictures. There are two different types of orbit where the satellites are launched into, either geostationary or near-polar. The two are very different and each have their advantages and disadvantages. The geostationary type are located around 36,000 kilometers above the equator and as a result maintain a fixed position relative to the Earth. The biggest advantage is that they have an excellent field of view, covering 1/3 of the Earth's surface. Also, a series of pictures taken from a geostationary satellite can be joined together in a movie loop to show development and movement of individual cloud features. However, they do have their disadvantages as well. Since their orbit is so high, picture resolution is usually less than from other types of orbit. Also, due to their location over the equator, geostationary satellite pictures give no coverage over the poles due to the curvature of the Earth. Polar orbiting satellites, on the other hand, orbit the Earth at a height between 600 to 1,000 kilometers, and therefore produce images that are much higher resolution. They can take excellent pictures over the polar regions, and are sun-synchronous, i.e., they cross the equator at the same local time. Each equator crossing is advanced westwards by around 25 degrees, completing about 14 orbits a day. However, polar orbiting satellite pictures do have their disadvantages. Since they are in a lower orbit, their field of view is considerably less, and they will not pass over the same region again for another 12 hours. As such, cloud features cannot be tracked. So, those are the two types of orbits satellite images can be taken from. But there are also several types of pictures which can be taken from the satellite's sensors. We shall examine three of the more common and certainly the most useful to aviation, but be aware that there are many more. Firstly, visible images. Basically, this is the image you would view if you were on the satellite. It's measuring radiation in the wavelength 0.6 to 0.9 micrometers, the visible spectrum. The brightness in the image will depend upon the solar elevation, the viewing angle, the reflectivity of the surface, sometimes called its albedo, and also on the resolution of the image. The albedo is probably the most important, so, ignoring the others and concentrating on this for the time being, a visible satellite image can be said to be a map of the reflectivity of the underlying surface. In general, thick cloud is more reflective than thin, and so will appear brighter. Water cloud is more reflective than ice cloud and will also appear brighter. And cloud composed of small droplets is more reflective than cloud composed of larger droplets. This is why fog appears very bright on visible satellite pictures, despite the fact that it's relatively thin. So, in summary, in a visible satellite picture, low reflectivity appears black, while high reflectivity appears white, with various shades of grey being used for reflectivities between the two. Most cloud will show clearly on the image, except when the underlying ground cover is snow or ice, or when thin cirrus is viewed against a light background such as a desert or lower cloud, i.e., when there is no contrast. Another common satellite picture is of radiation in the wavelength range of 10.5 to 12.5 micrometers, that is, infrared imagery. The interpretation of the infrared image is more straightforward. The degree of whiteness can simply be taken as an indication of the coldness of the underlying surface. It therefore has the obvious advantage that it can be viewed at any time of the day and does not require the sun to be shining upon the surface, unlike visible images which can only be viewed during daylight hours. Basically, in infrared imagery, the highest radiance comes from the warmest surfaces and will appear black, whereas the lowest radiance comes from the coldest surfaces and will appear white. Intermediate radiances will appear on a grey scale between the two. This table gives an indication of how to interpret visible and infrared satellite images. If it is possible to use both images together, then this can often be very useful in identifying the location of surface fronts, upper ridges and troughs, the stages of the development of depressions and tropical cyclones, as well as individual cloud types. It's also possible to estimate the wind structure and stability of the atmosphere, the presence of lee waves, the extent of snow cover, and location of sea ice. So now let's take a look at a couple of examples and see what we can determine from these images. This is a visible image taken from Meteosat, which is a geostationary satellite centered above the equator over Africa. Here we can make a rough estimate of the surface synoptic situation. We have low pressure centers located here, here, and here. A small frontal system is located around the low pressure over southern UK, with a warm front, cold front, and occlusion. This system becomes a little more complicated because it joins up with a new one which is developing here. Now we can see the same picture, but using the infrared channel. Here we can see the same features that we did on the visible, but it is also easier to make out another frontal system to the north, which was a little vague on the visible picture. The one other type of satellite image you may come across is that of water vapour. These images are a measure of radiance in the wavelength of 5.7 to 7.1 micrometers, the region of the spectrum where water vapour absorbs strongly. Darker shades indicate that the upper atmosphere is drier, whereas lighter shading shows higher levels of humidity in this region. Water vapour images are not usually as clearly defined as other types of satellite imagery. However, there are instances where clear delineation between high and low humidities occur. One of these can sometimes be found where moist air from a large cumulonimbus cloud penetrates into the drier stratospheric air. This normally occurs in the tropics. The other occasion can be seen on the poleward side of the polar front jet, where the moist cirrus-laden air beneath the tropical tropopause abuts the dry stratospheric air overlaying the polar tropopause. So in this water vapour image, we can identify the position of the polar front jet here. Satellite imagery is not only useful for looking at cloud structures. There are several other parameters meteorologists will measure from them. For example, winds can be derived by tracking the movement of clouds from consecutive geostationary images. Also, by comparing the infrared image with the temperature profile of the atmosphere, the temperature, and hence the height of cloud tops, can be determined. Similarly, where there is no cloud cover, the sea surface temperature can be calculated. This particular image shows sea ice. You may occasionally come across satellite pictures called false colour images. These tell us exactly the same information as grayscale images, but use colours. So that's it for remote sensing. The data provided by these techniques can be a useful aid, giving more comprehensive information over a wide area, particularly in data-sparse regions.